What a raster is, in the simplest form, is a grid of cells, of columns and rows that go across, and then each cell has some data in it, and then that's georeferenced to the Earth. We call them pixels. A lot of times when you're talking computer language, one of the things about rasters or cells is each pixel or each cell contains one piece of data, contains one number. So it could have the amount of rainfall in that square, but it wouldn't tell you slope, it wouldn't tell you soil type, it wouldn't tell you anything else on that land. Okay, it's only going to tell you one thing. So there's one of the downsides of raster analysis is you got to have a layer for every data in that table. You used to have a table with a bunch of columns. Each column would have to have its own raster file. Now, the advantage of this, on the other hand, is it's much faster. Since I only have to analyze that one number in that raster, typically raster analysis is a much faster type of analysis and works much quicker than vector analysis, which is pulling in a lot of different aspects there. So one of the aspects of rasters. There's a couple types of raster data out there. One of them is a discrete raster. Land use would be a discrete raster. I've got land use 10 here, and then I got land use 14, and then I got 13, and that whole area is the same. Fairly discrete, fairly substantial areas possibly. Roads actually would be another type of discrete raster. Here I have the primary roads in brown, the secondary roads in blue, and then everything else has no data in it. Okay, so that's a discrete raster. The other type of rasters are continuous. And there are two types of continuous. Probably the one you're going to see the most of or work with the most, or at least put in your maps, are images. An image is a continuous raster because every pixel, every cell continuously changes as you go through. There's no blocks of cells together. It's just continuously changing one direction or the other. One of the more common ways of using continuous rasters is with DEMS. And DEMS are digital elevation models. So they basically have the altitude in every single block, and you can do a lot of neat analysis with DEM rasters. Images, there really isn't anything to analyze when you look at them typically, but they make good backgrounds, depending on the type of image for that matter. Now, when we're talking about images, typically, unless it's a black and white image, you're going to have several bands coming in. Here we got a Landsat satellite image. It's got actually 7 different bands. So when I bring that file in, there's actually 7 files that are coming together and locking together when you bring it in to form the colors. Typically, with most color folders, you're going to work with 3 bands. Okay, so that's something to realize a little bit is when you're bringing in an image file, unless it was something that was scanned, but if it's like a Landsat or something like that, a lot of times those have separate bands for the different colors, which has some advantages of the analysis and things, and some confusion sometimes bringing files in. You can also scan an image in, scan a map in, bring a picture in from the internet and lay it behind there. That's an image file, but that's not going to have your 3 bands and such in it most likely. Why use rasters? They're better at storing certain kinds of data. They're better at analyzing certain kinds of data, often faster, as I've mentioned, than vectors. And imagery is quite often desired. Many of you are going to have a project where you're going to do a farm or something like that, and you're going to outline your field boundaries. Well, obviously you want an image behind there to outline those boundaries. So that's a raster file there, although we're not analyzing it, we are using it. Keep in mind though, precision is generally lower because now we're gridding it. Okay, instead of drawing a line around a vector, we got blocks all over. If you want more precision, you just make smaller blocks. The smaller the block, the more storage I need, the more memory I'm using up, the slower things are going to run. So bigger blocks are better, but it's not very precise. And the other thing is you cannot store multiple data in each raster. You have to have multiple rasters for multiple data. So what is this block size, this resolution? That's basically a cell size dimension. Left-hand picture there, you see a vector format where all the lines are drawn, fairly simple. It doesn't use a lot of memory because all it's got to remember is the line. Well, if we take that same file and put it in a 200-meter raster, okay, we got the lines on the edge, but everything on the inside has got cells of data in it also. Okay, so there's more data there as you look at that as far as cells, but each cell only has one bit of data. But you notice as you look at that center picture there, it's kind of jagged and doesn't flow smoothly, doesn't look very accurate. So what we'll do is, okay, rather than have a cell that's 200 meters by 200 meters on the ground, let's make it 50 meters by 50 meters. That takes 16 times as much memory, okay, when we look at it. So it's a square of the resolution if you want to look at how much bigger it is. A lot of people would really get a nice picture, and if you bring down a digital orthophoto from the internet, you get about a 1 meter by 1 meter. Those are huge files if you take any kind of area in. You got to limit that to a small area, one small farm or something like that if you're bringing a file like that in. So that's one of the downsides of rasters. Raster analysis uses the cell-by-cell functions in one or more input grids. When we're throwing these grids together, they really need to be the same. Our older software, not ARC-10 for that, but older type software, you have to ensure that they're exactly the same when you bring them together. Newer software is automatically going to do some adjusting. We'll talk about that. That's what we call resampling. For example, you've got the grid on top. I layered two grids together there. One's black outlines and the other's underneath. By resampling, I form the new grid down below. Okay, and that's not exactly true. It doesn't represent the true world of what we started with on top there, but it does get it into a raster that will match now to the grids. There are three main ways of resampling. One is the nearest neighbor. So what I do is I take the center of the cell, and that becomes my new raster. This is okay when you want the original data values to be preserved. Okay, you want exactly the same. In other words, I don't want to average anything together. I want to use the same number that was before. It is the fastest method because it just grabs a point, grabs the data with that point. Another second method is bilinear resampling, and what it does is takes that center dot and then takes the next four cells around it. The farther away a cell it is, the lower weight it gets. So then it averages those four cells together and gives you something. Good for continuous data such as elevation especially. And then cubic convolution resampling, very similar to bilinear but takes in a whole lot more data. Again, good for continuous data as far as elevation, but a much more time-consuming method of analyzing, particularly if you're analyzing a very large raster. Caution, ArcGIS automatically resamples. When you bring two rasters together, it's going to do the resampling to make sure they match up. It's not going to warn you because sometimes this resampling can degrade the information in that raster. You need to be aware that's happening. Best practice, before you bring rasters together, strive to create and keep the analysis data aligned. In other words, try to get the rasters the same when you create the data. Use your environmental settings to enforce some things. We talked about environmental settings in our last chapter. Use available resampling functions to prepare your data so that you're controlling it. Okay, so you resample before you bring the things together. ArcGIS is going to resample automatically, but if you have control over it, you can decide how you want to resample. So some things to keep in mind about that issue. Map algebra is something we're going to do with rasters. Essentially, basically, they're just an array of numbers. You've got two grids there, input grid 1, input grid 2. Line them up, match them vertically, and in this case we can add them. I don't know what they did in this example, but you can also subtract, you can multiply. There's a lot of different things you can do with map algebra depending on what you want for results. Here's an example of map algebra. I've got precipitation in centimeters on the left hand side. All I do is multiply or divide that by 2.54, and then on the right hand side it converts it to inches. Another way we can do it is model some equations. For example, here I've got precipitation and slope. Divide that by erosion minus my vegetative cover. That's going to give me a hazard index for soil erosion. Okay, so I put those numbers together. Basically, I got four different rasters. I got a precipitation raster, I got a slope raster, I got a erode raster, and I got a vegetative cover raster. Okay, and I can put all those together in this formula that you're looking at here and get a model that shows me, okay, where's my most concern at. Boolean rasters, you're going to work with Boolean rasters when you do the tutorial and work with that. Boolean rasters, basically they return a 0 or a 1. So for example, I'm only going to be concerned with slope that's less than 10 degrees for the situation that I'm making an analysis on. So I put a Boolean raster in there, and the left hand side's got all the slopes in. The right hand side, it's a 0 or a 1. A 0 is a 1 is true, which means it's less than 10 degrees. A 0 is false, which means higher. Okay, and I can eliminate then the falses if I want through a process here. Boolean rasters are essentially 4 types. It can be A and B, and then it's only going to include those things that are in common for both. It can be A or B, which includes everything from both. It can be A, X, or B, which means it's everything that does not be not in common, same as intersect from our previous chapter, or A, not B, which is very similar to what we did with union before. So that's how we can do some raster analysis. So here, if we do a Boolean overlay of and, it's going to take our precipitation and our elevation, put them together, and you notice the only thing that's left in our logical habitat is one that's in common with both. Here's the example of the raster calculator you're going to be working with. You're going to type expressions in there. Make sure, by the way, when you do the raster calculator, check your output raster there at the bottom, and make sure you might have to have that browse folder at the end to make sure you put it where you want it to be so you don't lose it. Other raster analysis techniques: reclassification, surface functions, distance functions, density, interpolation, neighborhood functions, zonal functions. Those are all things we can do with our raster analysis tools. Reclassify, we have our slope, and that's the example already given. I want to basically reclassify it into high slope and low slope. Surface analysis using digital elevation models, a lot of things we can do with that. Keep in mind, a DEM is a whole bunch of grids. Here's a grid that's 2,000 feet above sea level. Here's one in 1999 above sea level. Here's one in 1950 above sea level. All those grids have a certain measurement above sea level. That's all they have. But by comparing that information together, I can figure out the slope, percent slope by the size of the grid in a different elevation. So that's one thing I can calculate from a digital elevation model. Another I can see which direction is it sloping to the south, the east, the north, the west because of the different altitudes. That's called aspect. So I can do an aspect calculation using the spatial analysis tool. I can do a hill shade. How's the sun going to be showing on that? Those are kind of neat little files when you do a hill shade on them and looking where the shadows and the light's going to be at. View shed analysis. In other words, my house is going to be right here where that pink dot is at. What can I see from my house? Okay, you can actually, by using a digital elevation module, what's in the way, what's below, what's in a valley, it's going to tell you what you can actually see from the location of that house. Pretty cool analysis you can do. Hydrological functions like streams, watersheds, where the water going to go. Distance function. I can figure out what's the least cost path. In other words, from point A to B, a straight line is the shortest, but if that goes over a mountain, it's not the easiest. So by using a digital elevation model, I can determine what's going to be the easiest. Euclidean distance. Basically what Euclidean distance is from a point to the next point, that's a line of sight distance to that. Creates a grid as far as how close things are to certain points. Kind of like creating a buffer. And Euclidean direction. Tells you what direction you are from a certain point as you did a raster analysis. Buffers. We've talked about buffers in our geoprocessing chapter, our previous chapter. You can do buffers with your spatial analysis. Interpolation. This is commonly, for those of you in agriculture, this is something commonly done with soils. When you go out and take soil samples, you may take it only in certain places. You don't take every foot a soil sample. Quite often now with grid sampling, we take about every 2 acres. We pull a sample out of the center there. And then the next 2 acres. Well, I have 2 samples, one in this 2 acres, one in this 2 acres. What about everything in between? Well, we use interpolation for that, okay? This is 20 parts per million, this is 30 parts per million. Well, okay, 20, 21, 22, 23, 24, up to 30. Sounds fairly simple, but it's a little more complicated than that. Here are precipitation values. Sample point features, different climate stations. The ones up the northwest corner at 36 inches, go a little bit south and east of that, and you got 57 inches. So we'll interpolate between those two. That's the kind of rainfall lines we have. This is typically how they do weather maps, by the way, is interpolation. They don't have weather data for every square mile out there. They interpolate something. Keep in mind, interpolation is not the truth. If we did an actual elevation map, which is on the left, and we interpolated that from only having the information from the summits, it would look like the right-hand side. And the right-hand side obviously is not the same as the left-hand side. So we've got to be careful. Okay, we're kind of taking a best guess of what's going to be the in-between values. There are several ways of doing it. Oh, well, let's look at neighborhood specifics. Next thing is neighborhood statistics that we can do a calculation on. In other words, I want to find cell 1, I want to find the minimum in that 9 block cells. Okay, so I got a 1, a 4, 4, 1, 1, 2, 3, 4, 3. Okay, what's the minimum number? So then that block would calculate what's the minimum of that area. I can do the same thing. Of the 9 cells I'm in the center of, what's the average? Okay, and it's 2.5. And you'll see each one of those on the right output grid has difference. It's the 9 cells that I'm in the center of. What's the average? So those are neighborhood functions. Advantage of using a neighborhood function, it kind of smooths things out a little bit. The larger the window size, the larger you're using for that. In other words, I'm using 9 cells, okay, it's going to be pretty accurate. I use the next largest, which is what, 16 cells. Okay, more cells. The more cells I interpolate that information from, the smoother it's going to be, but probably less accurate. I can do neighborhood statistics over and over. I can do it once, and then come back and do it again, and it will again try to smooth it out. So it's a way of smoothing things out and making them look a little better and maybe a little easier to analyze. Before a 5x5 majority filter, after a majority filter, as we're looking at it. Again, it smoothed out a lot of areas. It probably a little too small of area to worry about anyway in my analysis, because I may be doing a little more. Example, I have a raster situation that we work for. Problem we have is finding a potential location for a new landfill. So what's important about landfill? Number one, it needs to be flat because we don't want it to run off from there. Less than 10 degrees. No more than 1 kilometer from any existing road because it's hard to get to. At least 500 meters from any existing stream, and I want it to be in an area that doesn't have a lot of trees, a meadow or a low density forest, so I don't have a lot of trees to clear off to make the landfill. We're going to use a Boolean raster for this. So first thing is, I'm going to do a slope function. Anything less than 10 degrees, I got my output on the right hand side there. Next is road distance. Anything that's less than 1,000 meters from the closest road. There's my green areas. Those are all within there. Next is stream distance. So I'm going to create a buffer on all my streams. I want a distance of greater than 500 meters from streams. So now we got my purple on my output raster there. And then the vegetative condition. I want the areas that are actually have low vegetative density. And that ends up being the blue areas there as we look at it. So find the areas. I basically do an and, slope and roads and streams and vegetation. So an and is like multiplying. So if I multiply 0 times 0 times 0 times 0, okay, I end up with 0. Multiply 1 times 1 times 1 times 1, I end up with 1. So all the 1s is where I should locate my landfill. All the 0s is where I should not. Another thing you could do is additive. Rather than multiply, you could add them together. And what's neat about additive, okay, let's say, well, yeah, I want to be in there, but I can't be there for some reason. Maybe the land's not owned, which would be another thing you could put in the model. But here I can actually ramp it. So 4 is the ideal places. 3 is okay, but it doesn't meet one of my criteria. And 2 meets 2 of my criteria, but not all of them. So another way of doing a raster analysis. Okay, that completes that lecture.